So let's go ahead and dive in. We'll minimize that. I believe this is the slide that we were covering tubes, and we were going to the path of airflow from the nasal cavity to the pharynx, to the larynx, to the trachea, to the primary bronchi, secondary, tertiary, and now we're these little tiny tubes. A bit larger than 1 millimeter in diameter. And as we look at these bronchioles, we still have ciliated epithelium. A key difference between the bronchial histology and the rest of the respiratory tract is that instead of being out of the respiratory tract, they still connect to that mucociliary escalator. And as we look at this branching process, there are many, many levels of branching. Eventually, we get to the end, and per lung, we'll have 50 to 80 terminal bronchioles. And as we look at the terminal bronchiole, which is present in this histogram I have on the screen up here, we can see a fair amount of smooth muscle within the terminal bronchiole. It's much thicker. As we get to the respiratory bronchiole, this small section right here, we find the layer of the wall becomes much thinner. It becomes so thin that we can start to have the diffusion. We can start to have respiration occurring. And then bronchioles eventually will lead into the smaller and smaller tubes, the alveolar duct and then the alveoli proper. One of the things that we note with the respiratory bronchioles is they are branch on the models, and you'll see these models in the lab today, directly into a cluster of alveoli. As we look at these alveoli, a common bad analogy used for alveoli, and that implies that there's one connection going to each individual alveoli, because if you think of a cluster of grapes, there's one little stem on each grape. That's not necessarily correct. One alveoli can be directly connected to all of its neighbors. It can be directly connected to multiple neighboring alveoli. It may on the surface look like a big bunch of grapes, but the key difference is that the alveoli have multiple pores in them that allow them to connect to the neighboring alveoli. So as we look at this respiratory bronchiole, it will connect to a larger alveolar sac, and that alveolar sac is made of multiple individual alveoli. As with individual alveoli, this is where most of our respiration will take place. We have most of our gas exchange between our lungs and our bloods taking place in the alveoli. And there's a very good reason for this. Our alveoli are made of a simple squamous epithelium. Our cilia, we want the membrane to be as thin as possible. And by making this membrane as thin as possible, we can really pack a lot of square footage into the alveoli. In terms of the surface area, we're looking at about 70 square meters. Most of you don't think in terms of meters. So another way to think of this is you have about 200, let's see here. There's about 9 square feet per square meter, 9 times 70. 9 times 7, give me a second, it's 63 plus 0. There's about 630 square feet in your lungs. Or you could think of the first story of a typical house. That's the surface area of your lungs. Now within our alveoli, the most common kind of cell is going to be, in my opinion, the cells that make up the wall. These flattened cells that are the simple squamous epithelium. They are known as the type 1 alveolar cells. But they aren't the only cells that are present. There's 2 other cell types we need to cover, the type 2 and then the macrophages. So let's look at type 2, great alveolar cells. Great alveolar cells are and serve a very important purpose. They secrete surfactant. And when we think of surfactant, I just want you to think of a biological soap. Chemically speaking, a surfactant or soap is anything that has both a hydrophobic and a hydrophilic region on it. So the molecule can be empathic in that respect. And these surfactant cells, or type 2 alveolar cells, are going to release our pulmonary surfactant. It's worth noting that these cells aren't weeks after conception. So if we look at prematurely born infants, typically before the 34-week mark, they don't have fully functional type 2 cells yet. We'll talk more about what the implications are in our next presentation. And then finally, we have the alveolar macrophages. These alveolar macrophages are what we use in lieu of the mucociliary escalator. We don't want a mucociliary escalator down here because mucus would clog up the respiratory membrane and slow the diffusion of gas. We want our membrane to be really really thin. And we also want to be able to remove stuff from this membrane. So if something makes it all the way down into the alveoli, we have alveolar macrophages that move around and phagocytize any dust particles that make it into our alveoli. In terms of how many of them we go through a day, we go through about 100 million alveolar macrophages a day, each one neutralizing multiple dust particles. If we zoom in really close, actually let's back up a couple slides here. If we look at our alveolus, in the corner we have, right in the center here in red, a blood capillary. And if we zoom in on that blood capillary, we find that there's the capillary with its tunica intima, then we have a basement membrane, and then we have the type 1 alveolar cell. So this respiratory membrane is 2 cells thick, 2 simple squamous cells thick. We have the simple squamous cell of the alveolar, and then we have the simple squamous cell of the blood capillary. And holding these 2 simple squamous cells together, we have some extracellular matrix, a basement membrane, just connected proteins, anchoring those cells together. And because it's so thin, we're able to very rapidly and quickly and deliver it into the blood and take carbon dioxide from the blood, lungs. As we look at our alveoli, we don't want liquid to build up in our alveoli. Ultimately, liquid in the lungs lowers or reduces the rate of respiration. It reduces the rate of gas exchange across our membrane. This is one of the reasons why drowning is bad for us. It's possible, go figure, but it's possible to drown even when you're not underwater. I'm thinking of my daddy. He drowned 3 days after and died in his easy chair. And what happened for him in particularly was fluid was building up in his lungs while he was at post-injury. And even though he wasn't being submerged, his alveoli were being filled with liquid, and he drowned in his own fluids, unfortunately. Now, within our lungs, we do have a system in place to help remove excess fluid that builds up in our lungs, and that's going to be the lymphatic drainage network. This lymphatic drainage network, or this network of lymphatic vessels and lymph nodes, is very effective from the lungs. So much liquid builds up in our lungs, and we're constantly producing lots of excess fluids with the type 2 alveolar cells. Our lymphatic drainage network is kind of a double. It does a good job of removing fluid buildup from our lungs. The downside of having lots of lymphatic networks in our lungs is that if we have any kinds of lung cancers develop, it spreads throughout the lymphatic network. We also find that there's a very low blood pressure in our lungs. The capillaries of the alveoli have a blood pressure less than 10 millimeters of mercury. And having this incredibly low blood pressure makes it so that these incredibly delicate membranes that are 1 to 2 simple squamous cells thick don't rupture and break. And then finally, we have the pleura. We talked about pleural membranes last semester. It's worth emphasizing them again. When we think of a serosa, it's a double membrane. The serosa around the lungs is called the pleura. As we look at this double membrane around the lungs, there's two layers. The layers against the lungs directly, the visceral pleura, and then the layer that's directly against the chest cavity or the thoracic cavity, known as the parietal pleura. And as we look at these two membranes, there's a little bit of space between them, known as the pleural cavity. And the pleural cavity is very important for multiple reasons. One is that we're going to have pleural fluid build up in this cavity. This is going to lubricate the lungs and allow us to expand and contract our lungs as we breathe in and breathe out. Reducing friction is a very key. It also is going to create pressure gradients. We want our lungs to be depressurized relative to the external environment. And these double membranes that are airtight help to keep us at negative pressure in our lungs. And we want that negative pressure so that our lungs do not deflate. Every once in a while, there'll be a puncture wound to a chest. You'll see somebody with a pneumothorax, that's what's called. And the pressure equalizes with the external environment. And instead of being a negative pressure, it's a pressure of 0, and then the lungs start to collapse in those situations. Another component of the pleura that's very helpful is compartmentalization. It helps to separate the lungs from the other organs and pathogens present within the thoracic cavity. And this is where I was hoping to get to last Thursday. So this is a click on target. This is a tougher question. I have to really think out of the box on this one. As we look at this question, it's asking if there's a breakdown of the mucociliary escalator, where would bacterial growth be most likely to develop? Another way of thinking of this is, where's the lowest point in the respiratory system? Where would mucus be the most likely to pool or accumulate first in our respiratory system? The lungs are not equally spaced in terms of elevation. One's a little higher than the other one. Let's go with 10 more seconds. 5, 4, 3, 2, 1. I like what I see. Some good responses here. So we're thinking about it critically, and that most of the responses are at the bottom of the lungs. When we look up here within the trachea and the larynx, mucus would not be very likely to pool in the trachea or the larynx because gravity would just keep pushing it down into the lungs. So the best responses are at the bottom of the lungs, and between the two lungs, one's a little bit higher than the other one. Our liver pushes on the right lung, and our right lung has a slightly higher elevation than the left lung. So as we look at these, the left lung is the single best location, just based on the mechanics. When I was making this question, I looked at several journal articles about pneumonia and bacterial growth in the respiratory system, and as it turns out, there's no actual pattern between left lung and right lung. They're both equally likely to get infected with pneumonia based on the literature, even though the left lung is just slightly lower than the right lung. So that's it for this presentation. Let's shift gears to physiology of the respiratory system. So let's talk respiratory physiology. Physiology, that's the function of the body part. Structure and function, very important in A&P. So we've spent a lot of time talking about the structures of the respiratory system. Now we're going to spend even more time talking about what they do. And there's going to be a fair amount of chemistry involved with this. While I was prepping our presentation, take time to read the chapters in the textbook. May have noticed that they talked about Boyle's law, Henry's law, Charles' law. I believe there's even a mention of the ideal gas law as well in the textbook for this chapter. I tried to minimize the quote-unquote chemistry gas laws, so I'm not going to give you a lot of the vocabulary, but we're going to still talk about principles, because the principles are what are really important in this situation. Now, as we look at our lungs, we can have ventilation. Ventilation can be the movement of gases, or conduction of gases. And there's two kinds of ventilation we care about: breathing in, inspiration, and breathing out. That leads to a lot of really bad puns within this body system about expiring and kicking the bucket. I won't share any of them with you. There's quite a few out there, though. As we look at our respiratory cycle, this is going to be the process of breathing in and breathing out. And there's some ways that we can breathe in and breathe out. Most of you in the room right now are pretty relaxed. You have quiet respiration. You're breathing in and out very hard. When you're physically exerting yourself hard, though, and you have a lot of effort being put forth, you're going to forcefully breathe in, forcefully breathe out. That's called forced expiration. This morning, it was about 3 in the morning, I was having trouble sleeping. So, for the heck of it, I tried having only forced expiration to breathe out. Tried only exhaling with my abdominal muscles to simulate having emphysema, and boy, it was tiring. It put me to sleep fairly quickly. Yeah, it's better than counting sheep. Now, as we look at the movement of air, I'll say this again because I remember as a student, it really confused me. Air is a fluid. Air is a fluid. Air is not a liquid. It's a gas. And this is a gas that flows. Therefore, it's a fluid. So when we think of the respiratory system, air will flow from areas of high pressure to areas of low pressure, just like blood flow in the cardiovascular system. And these pressure gradients are what allow for us to move air in and out, to inspire and expire. So, in terms of what the single most important muscle is for breathing in and breathing out, it is the diaphragm. It's the prime mover. As we look at our diaphragm, it starts at the bottom or inferior margin of the rib cage and then arches upward towards the heart. Now, with muscles, when we contract a muscle, the fibers get shorter. So if we were to take the diaphragm and make these muscle fibers shorter, to make them shorter, we would have to have them go straight across and lower the diaphragm down. And this process of contracting the diaphragm and lowering it causes the volume of the thoracic cavity to increase. This lowers the pressure in the thoracic cavity and causes air to rush inward. Our diaphragm accounts for the majority, over half of our airflow. When we go to breathe out, our default action is just to relax, and we'll spontaneously breathe out. Especially in this room, we have a lot of young, healthy people. You have lots of elasticity to your lungs. So by default, they'll exhale when you stop trying. Breathing out should and is a lazy thing to do. We don't want to try to breathe out. Otherwise, that's a lot of work. There's some other muscles, though, that we use to breathe in and breathe out. We have external intercostals. And external intercostals primarily are going to be used for inspiration. So when we think external intercostals, the muscles in between the ribs, inter for in between, costal for rib, they are going to take our thoracic cavity, in particular the ribs, and they're going to cause the ribs to be elevated and raised upward. And by taking our ribs and raising them upward, we cause our thoracic cavity to increase in thickness. So by making our thoracic cavity thicker, we increase its volume, and then lower the pressure, and cause ourselves to breathe in. So between the external intercostals and our diaphragm, that's the vast majority of the airflow. There are some secondary muscles that we use. For instance, there's the scalenes that help to elevate the top two ribs. But overwhelmingly, I want you to fixate on the diaphragm and external intercostals for inspiration. And then we have expiration. Quiet expiration, breathing out when you aren't trying hard, is all about relaxing. The elasticity of your muscles, of your lungs, the recoil of your muscles forces air out of your thoracic cavity. The thoracic cavity decreases in volume. As the volume goes down, the pressure goes up, and air will flow out. Let's talk about breathing out with forced expiration. There are multiple muscle groups that we use to force air out of our lungs. The two biggest, or the two most important, are going to be the rectus abdominis, your abdominal muscles, the six-pack muscle, and then also the internal intercostals. As we look at these, there are some other muscles as well, including the obliques, and to a very small degree, the external intercostals also help us breathe out, but the internal intercostals and rectus abdominis overwhelmingly help us to exhale. So when we contract these muscles, they lower the ribs, and they cause our thoracic cavity to decrease in volume. The internal intercostals cause the ribs to go down. Contracting the rectus abdominis pulls down on the clavicle, no, not clavicle, sternum, and pulls the thoracic cavity down and reduces volume. And it's forcefully reducing volume, and forcefully increasing the pressure in our lungs and getting the air out of our lungs. Those of you who are maybe you're in vocal jazz or choir or something of that nature, some kind of organized singing, most choir teachers will tell you to belly breathe. And the reason they want you to breathe with your belly or contract your rectus abdominis when you're singing is you can force more air out of your lungs and be able to sing more words before having to pause to inhale. Regulate breathing. We use some parts of our brainstem. Thankfully, this is a voluntary process. It should be an involuntary process. So we don't have to think about it. We breathe automatically. Within the medulla oblongata of our brainstem, so here's our medulla oblongata, right down here, we're going to have the ventral respiratory group and the dorsal respiratory group. These are just two clusters of neurons that help to regulate our respiratory rhythm, help to regulate breathing in and breathing out. And of these two clusters of neurons, the ventral respiratory group is the most important for generating our respiratory rhythm. That ventral respiratory group and the dorsal respiratory group work in conjunction with each other to cause a contraction of the diaphragm and a contraction of the external intercostals. The nerve that they use to control the diaphragm is the phrenic nerve, which is a branch of our vagus nerve. As we look at the pontine respiratory group, which is going to be located within the pons of our brainstem, that pontine respiratory group allows for us to have special adaptations. Maybe you want to sing, maybe you want to laugh, maybe you want to talk. To have special movement of air in and out of your respiratory tract, our pontine respiratory group will send a signal that modifies the respiratory rhythm that's regulated within the ventral respiratory group. You've probably seen somebody who's hyperventilated before. Hyperventilation is too much breathing, too much movement of air in and out of the lungs. And you oftentimes will see them with a paper bag up to their mouth. And there's a very important reason for that paper bag being put up to the mouth. When somebody's hyperventilating, they are getting rid of too much carbon dioxide from their bodies. Believe it or not, carbon dioxide can be a good thing. In moderation, we need just a little bit in our bodies. And that little bit of carbon dioxide in our bodies helps to regulate our blood pH. If we're hyperventilating, the carbon dioxide is leaving too quickly, our blood pH is going to be altered, and then we can feel dizzy, we can start to pass out. Some not good neurological things happen to us as we have an alteration of our blood pH and cerebral spinal fluid pH. We put the paper bag in front of somebody's mouth when they're hyperventilating because it causes them to rebreathe their carbon dioxide. They breathe it out, and then they breathe it in. So they can help to maintain the correct concentration of carbon dioxide in their body while they're hyperventilating. There's also a strong psychological component to the paper bag. Usually when somebody's hyperventilating, they're experiencing some kind of emotional distress. Something bad has happened, and they are freaking out. And giving them the paper bag to focus on. Make it big, make it small, make it small. A lot of times they can fixate on the paper bag and stop fixating on whatever it was that was causing them the emotional distress. And a lot of times that will just cure the hyperventilation. Now, in these situations, when we have hyperventilation, and you're telling the patient the bag, make it big, make it small. You're asking the patient to activate their voluntary respiratory centers. Now, when we think of these parts of our brain, and I'll fill in the blank for you right here. Sorry about that. There was a formatting error. Within our higher brain, our cerebrum, where we house the conscious parts of our brain, we can decide, hey, I want to hold my breath. Hey, I want to breathe in and out very deeply. We can have some conscious control over those skeletal muscles that we use for inspiration and expiration. And in order to consciously control those skeletal muscles, we have to bypass the pontine and medullary respiratory groups. And we'll take a signal from the motor cortex of our brain and skip the brain stem entirely and go down to the spinal cord. And to skip the brain stem entirely, instead of using the reticular formations within the brain stem, we're going to use a separate formation called the cortical spinal tract, just a separate branch within our brain stem and spinal cord, to then directly control the skeletal muscles of breathing in and breathing out. And you can consciously hold your breath for a short period of time. The kicker is your brainstem is constantly monitoring your blood chemistry. And the longer you hold your breath, the more carbon dioxide builds up in your blood. And as you have more carbon dioxide, you have more acid, and your blood chemistry is altered more and more and more. And your brainstem at the beginning goes, hey, I'm not comfortable with this. This isn't cool, but I'll go along with it. And then as you hold your breath longer and longer and longer, the brainstem is going to be increasingly activated. Those respiratory centers in the brainstem are going to be sending stronger and stronger signals in response to the blood chemistry going farther and farther away from homeostasis. And instead of having kind of a weak signal, the signal becomes overwhelmingly strong from the brainstem, overrides the higher brain functions, and forces us to breathe in and breathe out. The breaking point is when our CO2 levels become so high that our blood chemistry, in particular our blood pH, becomes so acidic, and the cerebral spinal fluid becomes so acidic that the brain stem can no longer tolerate it and will override the higher brain center. As we look at the movement of air in and out of our respiratory system, air will flow from areas of high pressure to areas of low pressure. And the flow of this air is going to be directly proportional to the pressure gradient. If we have two equal pressures, there's not going to be a very rapid flow of air. But if we have incredibly high pressure right next to an incredibly low pressure, there will be very rapid movement of air. So as we look at this, remember, think back to that fluid flow equation you had to memorize for a lab, where we have the pressure difference on the top in the numerator, and then we have resistance to flow in the bottom, in the denominator. So as we have a larger pressure gradient, we have increased flow. As we have increased resistance, we have decreased flow. When we look at the air around us, air at sea level is defined as 1 atmosphere. It's also defined as 760 millimeters of mercury. And we find that the lower we go, the closer to sea level we go, the higher the air pressure. Has anyone in here had a chance to go to Death Valley, just out of curiosity? You should try it sometime. It's kind of neat. My plan is to go there over spring break. I had some siblings who went there. And one of the things I'm really excited to do at Death Valley is to take a pop bottle. I'm going to take this 2-liter pop bottle, squeeze it half empty, and pull it on really tight. Because I've been told in Death Valley, you're below sea level, you're above regular atmospheric pressure. And theoretically, if you take a mostly empty pop bottle with an airtight seal from Death Valley, and you bring it up to the higher elevations of Wisconsin, it will start to expand as you put it into a lower pressure system. So that's my goal for Christmas break. We'll see if it happens. The lower we go, the higher the air pressure. The higher we go, so the top of the mountains, the lower the air pressure. As we look at pressures, they can be described by something known as Boyle's law. And this is one of the few situations where I kept the name of the law, Boyle's law, that looks at the relationship between volume and pressure. When volume goes up, pressure goes down. When volume goes down, pressure goes up. They're inversely related to each other. So if we have an increase in our lung volume, we are going to have air flowing into the lungs. Air moves into the lungs because we have low pressure in the lungs when the volume increases. And then if we have either quiet expiration or forceful expiration, whatever the reason, if the volume of our thoracic cavity goes down and our lungs go down, the pressure goes up. And if the pressure goes up, air goes out. These pressures that we're looking at are going to have different names for different parts of the lungs. The intrapleural pressure is going to be the pressure in between pleural membranes. So within the pleural membrane, intra meaning within, what is it within? It's within the pleural membrane, or that double membrane. So that pressure within the double membrane is the intrapleural pressure. And that intrapleural pressure needs to be slightly negative. It needs to be a little bit less than 0 millimeters of mercury. And that causes there to always be some residual volume to our lungs. That means our lungs will always try to stick to the side of our thoracic cavity. The recoil of our lung tissue, or the elasticity of the lung tissue, is also going to work with us. Now, within this intrapleural pressure and with our pleural fluid, it's going to pull the lungs out against the ribs. And then the elasticity of the lungs are going to pull the lungs back in. And there's a tug of war, some give and take. And usually, we have some equilibrium. And the equilibrium is going to be the resting volume of your thoracic cavity. So there's a volume of your chest when you're at rest. That's the equilibrium volume. That's based off of the intrapleural pressure of your lung tissue. As we look at it, you can look at this diagram and see how there's the pressure pulling out, the intrapleural pressure pulling the lungs out against the rib cage. And then there's the elastic recoil of the lungs trying to pull the lungs away from the rib cage. And what we find is that within these serous membranes, there's a lot of cohesion between the tissues. We find that there's a lot of hydrogen bonding between the water molecules bound to the surface of these membranes. And that cohesion, or surface tension of the water, helps to keep the lungs stuck to the outside of the rib cage. As we are looking at the visceral pleura, the inner line of that membrane is going to cling to the parietal pleura. And as the visceral pleura is clinging to the parietal pleura, it's going to stretch the alveoli open and will increase the volume of an individual sac inside the lungs, increases the volume of an individual alveoli inside of the lung. And as that individual alveoli has an increase in volume, it has a decrease in pressure, and air flows into those individual alveoli. And at a gross level, at the macroscopic level, the lungs get bigger and air flows into the lungs. We inspire. Something else that causes our lungs to expand, or that is going to be thermal expansion. You've all seen a hot air balloon. Air has a tendency of expanding when you heat it up, and as you heat it up, it expands, becomes less dense, and hot air balloons float away. Within our lungs, air will go from about 20 degrees Celsius to about 36 degrees Celsius as we take standard air temp or standard temperature outside of our lungs and breathe it in. And that is meant to be a 7% increase in volume. So as we look at this thermal expansion, a 15 degrees Celsius increase in air temperature causes the volume within our lungs to increase about 7%. So we have the pressure gradients causing our lungs to expand. We also have thermal expansion. As we inhale the air expands just a little bit inside of our lungs. Now, as we're breathing in and breathing out, just a little change within our rib cage, just a little change in the orientation of our rib cage can cause an enormous change in volume. When we think of volume, it's height times length times width. So if I increase my dimensions 2 centimeters wide, 2 centimeters thicker, centimeters higher, 2 by 2 by 2, 2 to the third power is going to be 2, 4, 8 times. It's going to be magnified very rapidly. And we find that just a couple millimeters expansion in each direction can increase our overall lung volume by half a liter. And this is what we have right now in the classroom with most of us. We have what I like to refer to as lazy breathing. We do the least amount of work possible in order to breathe in and breathe out. So we'll just expand our rib cage just a little bit, breathe in just enough to get enough ventilation, just a little bit. And breathing out of just a little bit is our baseline breathing. During our relaxed breathing process, as we're breathing out passively, we're going to have compression of the diaphragm, and elevation of the ribs as we contract our external intercostals will cause the lungs to increase in volume. Then, because we're relaxed and we're trying to take the easiest approach possible, we just stop trying. We stop contracting, and automatically the elastic recoil of our lungs and skeletal muscle tissue. If you ever watched an action movie or some kind of a movie with this dramatic death scene in the movie, with the dying individuals always breathe out. They never breathe in with their dying breath. Because exhaling, breathing out, is a very passive process, particularly relaxed or quiet expiration. If we decide to force air out of our lungs, so we have active or forced expiration, we'll contract the internal intercostal, contract the rectus abdominis, and some other accessory muscles, and increase the pressure in our thoracic cavity and within our lungs 500 millimeters of mercury. And that pressure gradient of 500 millimeters of mercury causes air to be forced out of our lungs very rapidly during forced expiration. Occasionally, though, our pressure gradients break down. If you've ever worked with somebody who had a stab wound or some kind of a fracture or opening thoracic cavity, they'll have what is known as a pneumothorax. For me in particular, the people that I've known that have had pneumothoraxes typically have been people who fell asleep in their tree stands during deer hunting season, and they hit the ground, cracked a rib, and the cracked rib fractured their pleural membrane, giving them the pneumothorax. The pneumothorax is the puncture itself that equalizes air pressure. And if we equalize air pressure, we no longer have negative intrapleural pressure, there's not going to be anything forcing the lungs open, forcing air to continually flow into the lungs. And the elastic recoil of the lungs takes over and causes the lungs to shrivel up. And that shriveling up, the collapsing of a lung, is known as atelectasis. And there's a couple of ways we can cope with this. If we seal up the puncture wound entirely, if we seal the pneumothorax entirely, just typical blood flow throughout the lungs will slowly remove gases from the intrapleural cavity and cause the lungs to reinflate. You can accelerate this process, though, a couple ways. In more modern medical facilities, sometimes you'll see a little tube shoved into the puncture wound, and they'll just, with a little vacuum cleaner, about the same pressure that you have in an aquarium pump, they'll suck the air out of the cavity and depressurize that side of the lungs and cause the lung to reinflate. If you are in a pinch, you can set up a three-way where you take a piece of plastic, and just any piece of plastic will work just fine. You tape three sides of it and leave one side open, and it forms a crude valve that allows air to go out of the hole but not back in, and it will help depressurize that side of the cavity. As we're looking at these airflow situations that we run into, there are a couple things that can cause resistance to airflow. And when we think of resistance to airflow, that's just going to be making it more difficult to move this fluid. We can have the diameter of the bronchioles change. Bronchioles are the tubes that carry air into and out of the lungs. If we have bronchodilation, the tube becomes larger. An increase in diameter causes an increase in radius, and increasing the radius causes airflow or fluid flow to increase to the fourth power. So bronchodilation and bronchoconstriction are very powerful ways to airflow into and out of the lungs. When we bronchodilate, air will flow in faster. When we bronchoconstrict, it's more difficult to have air go in and out. Bronchodilation is associated with increased airflow, and we want that increased airflow typically in situations that are stressful or that involve activation of the sympathetic nervous system. So we find that epinephrine or sympathetic activation in general is going to cause bronchodilation. It's going to help us to get ready for a fight or flight response. Bronchorestriction or bronchoconstriction is going to make it more difficult to move air in and out of the lungs. This is going to be associated with the opposite of the sympathetic. We have the parasympathetic nervous system, histamine, which is associated with allergic responses. Cold air can also cause bronchoconstriction. If we have too much cold air entering our lungs too rapidly, it can actually cause frostbite to occur within the alveoli. Not a pleasant experience. It's fairly rare, though. My wife was telling me that when she ran cross-country for the WEAC conference, that if negative 5 degrees Fahrenheit or colder, they would cancel the meet, and they wouldn't let them run outside. So that's her guiding principle. She'll leave me alone, and I don't have to go running with her if it's colder than negative 5 Fahrenheit. But if it's warmer than that, she's like, come on, get outside, go, go. Some other things can cause bronchoconstriction as well, including chemical irritants. The most common one that most people think of is pepper spray. The capsaicin within the pepper spray causes irritation of the bronchioles and bronchi and causes them to constrict. Another way that we can increase resistance is by monitoring or changing, I should say, pulmonary compliance. Pulmonary compliance can be thought of as elasticity of the lung tissue. How stretchy is it? If it's really stretchy and has a lot of elastic recoil, we're going to have a lot of compliance, and it can expand and contract easily. Compliance goes down in a couple situations. We can have a disease state that will cause elastic tissue to be degraded. We could have a disease state that causes the buildup of scar tissue, which is not stretchy. Or we can have a reduction of the amount of surfactant. Surfactant is that biological soap produced by the type 2 alveolar cells, and it allows for a reduction in the surface tension. It breaks the hydrogen bonds that causes the sides of the alveoli to stick together. So what we find in these situations is that individuals that have enough surfactant have an easier time expanding their lungs. Prematurely born infants that don't have fully developed type 2 alveolar cells yet don't have surfactant, and they're born with a condition known as respiratory distress syndrome. And to get around that problem, a nebulizer will be given to those prematurely born infants, and they'll inhale aerosolized surfactant. or for lack of a better term, they'll take soap, put it in a mister, and have the child breathe it in. And that allows for them to expand their lungs easier by reducing the amount of hydrogen bonding, holding individual alveoli together. Now, air in the alveoli is air that we care about. That's the air available for gas exchange. That's the air available for respiration. And as we look at the air that we breathe in and breathe out, not all of the air makes it into the alveoli. Some air that's left over in our nasal cavity, in the pharynx, the larynx, the trachea. And we have leftover air in the conducting zones of our respiratory tract. This leftover air in a typical person is not available to get into the bloodstream because this area can't have gas exchange. We refer to it as anatomic dead space, or anatomical dead space. The anatomical dead space has some very real implications for us. If we extend the anatomical dead space, you have to breathe in and out with more effort in order to get enough air to your alveoli to have enough gas exchange. The best way to extend the anatomical dead space is to put a snorkel in your mouth. When you put a snorkel in your mouth, you're snorkeling, you're in a fabulous vacation, the snorkel in your mouth extends your airway, and you can't have gas exchange with a snorkel in your bloodstream. And consequently, when the snorkel's in your mouth, you have to breathe in and out harder in order to get fresh air to the alveoli in the middle of your lungs, or at the end of your respiratory tract. Ruby? Theoretically, yes. So you have to give them a crazy long snorkel and trick them into not spitting it out. So what we find is that for people that are near the surface, they can get away with a snorkel, but those individuals that went in traditional scuba tanks, they had to have one tube pumping fresh air down and a separate tube pulling the expired air away, because a snorkel would have extended the respiratory dead zone, or anatomic dead space, too much for them to breathe in and out appropriately. When we look at the anatomic dead space, sympathetic dilation, causing those bronchioles to get wider, does increase the dead space. However, we have multiple variables at play. So yes, the dead space increases, but airflow also increases at the same time and more than compensates for the increase in anatomical dead space. To measure the flow of the air in and out of the lungs and indirectly measure the anatomical dead space, you use a device known as a spirometer. It's a gross measurement of the air that goes in and the air that goes out. And as we're breathing in and out, as we have inspiration and expiration, there are some volumes that we look at. Volume. This is the lazy breathing, or shallow breathing. With our tidal volume, it goes in and out repeatedly and rhythmically, like the tides of an ocean. For most individuals, the tidal volume is 500 mils. And then we can have that inspiratory and expiratory reserve volume. If you're breathing lazily, you're relaxing, you're breathing in and out. At any point in time, you could cough like that person did. And that spontaneous coughing is going to force a ton of air out of your lungs. And that air that you can force out of your lungs while you're going through lazy breathing is known as the expiratory reserve volume. And then you also can have the air that you can breathe in at the drop of a dime. That is the inspiratory reserve volume. And most of us find that even though we have our shallow, lazy breathing, we still have some extra room in our lungs. We can still puff up our chest and breathe in a little bit more. So as we look at our spirograph, or spirograph, potato, we find our tidal volume, or tidal capacity, is a small fluctuation in the volume of our lungs. And then when you exhale forcefully, the volume of the lungs will drop down. This change is the expiratory reserve. And when you inhale forcefully, you are going to have the volume of your lungs go up dramatically. That's your inspiratory reserve. As we look at this individual right here, they were breathing in and out lazily, and then they breathed in, and then they breathed out forcefully. In other words, right here, it looks like they coughed because we have a forceful inspiration followed by a forceful expiration, or dramatic change in their lung volume. Now, our lungs will always have leftover air in our, and the reason we always keep just a little tiny bit of leftover air in our lungs is to minimize the amount of hydrogen bonding within the alveoli. If we completely drained all the air out of our lungs, the alveoli would completely collapse, and there'd be lots of hydrogen bonds within the water molecules holding individual alveoli together, making it really difficult to reinflate the alveoli, despite the fact that we have surfactant in our lungs. That little tiny bit of leftover air is known as the residual volume. And if you breathe in and breathe out and force as much air out of your lungs as possible, you still have just a little bit of air for gas exchange. You don't pass out instantaneously. You will quickly, but not instantaneously. That tiny bit of leftover that you're still doing gas exchange with is the residual volume. As we look at the vital capacity of our lungs, the vital capacity is going to be the maximum amount of air that you can have go in and out. It's going to be the maximum amount that you can change the volume of your lungs, assuming no pneumothoraxes. So if we look at vital capacity, respiratory reserve volume plus the tidal capacity, or excuse me, tidal volume plus the inspiratory reserve volume. The bigger your vital capacity, the longer you can hold your breath. The more you can take air and hold it in. And then as we look at the vital capacity, it's going to be directly related to the inspiratory capacity. So remove this expiratory reserve volume and focus just on tidal volumes and inspiratory reserve volumes. This is going to be the most that you can inhale at a given point in time from your resting point. Let's go back to the spireograph. The vital capacity is the maximum amount that you can breathe in and breathe out. Inspiratory capacity is just the maximum amount you can breathe in after tidal volume, or easy breathing. And if you take all of these volumes and combine them together, in particular, if you take, let me clean this up, there we go. If we take vital capacity and add it to residual volume, we can get the total lung capacity, or the total amount of air in the lungs that can be stored in the lungs. And then as we look at our functional residual capacity, our functional residual capacity is going to be calculated by taking our reserve volume and our expiratory reserve volumes and combining them together. From the graph, let's clear this up, it's going to be the maximum amount that we can forcefully exhale, the expiratory reserve, plus residual volume, giving us the functional residual capacity. These variables or calculations we should be able to calculate. Now, as we look at this process of measuring the amount of air that goes in and out of somebody's lungs, it's really important because we can use the changes in volume to diagnose diseases that the individual may have. If the individual has a restrictive disorder versus an obstructive lung disorder, think back to our physio-X activity, restrictive versus obstructive diseases, we are going to change how they breathe in and breathe out. When we think of restrictive disorders, they reduce pulmonary compliance, or more broadly speaking, they make the tissue stiffer. Restrictive disorders increase the stiffness of the pulmonary tissue. And if we lose elasticity to the lungs and we lose the ability to expand our lungs, to inflate, and then we are going to scar tissue or fibroses develop. Within the lungs, two classic examples of disorders include black lung disease and tuberculosis. Thankfully, in the United States, there's not that much black lung disease anymore. When people spent years in the coal mines of Pennsylvania or in the Appalachian Mountains, as they breathed in coal dust for years and years and years, that coal dust would overwhelm the alveolar macrophages and cause the alveoli of their lungs to be choked with charcoal or coal, and their lungs would turn black over time. And they would lose the elasticity of their tissues and have trouble inflating their alveoli. Within the United States, thankfully, we don't have a lot of tuberculosis, although it is alarming to me that within the Russian prison system, Southeast Asia, and South Africa, there is pan-resistant tuberculosis or tuberculosis-resistant antibiotic in existence, rapidly spreading throughout those regions of the world. When somebody is infected with tuberculosis, which is highly contagious, unfortunately, we find that they'll have a little nodule appear in their lung. That nodule grows to form a large region of scar tissue, and they have, for lack of a better term, large regions of empty tissue surrounded by non-compliant fibroses build up in their lungs. They lose the ability to breathe in. And as they have these diseases, this bacteria grow in their lungs, they cough a lot, and the constant coughing associated with tuberculosis is what causes it to spread very rapidly because it travels through the air. We can have an obstructive disorder. When we look at obstructive disorders, instead of affecting the flexibility of the lung tissue, we're going to block the tube the air travels through. We obstruct the pathway of airflow. So as we look at obstructive disorders, they include anything that can cause a narrowing of the bronchi or bronchioles. That can include asthma or just general inflammation of the bronchi, bronchitis, chronic bronchitis in particular. When we look at emphysema, it's kind of an in-betweeny weenie. Sometimes it's categorized as an obstructive disorder. Sometimes emphysema is categorized as a restrictive disorder. It does a little bit of both. Emphysema causes there to be a loss of elastic tissue within the lungs. That loss of elastic tissue within somebody who has emphysema means that for them to breathe out, they have to contract their abdomen. They want to exhale. And that gets very tiring very quickly. And these individuals that have emphysema also have some fluid buildup in their lungs as well and some mucus buildup that acts as an obstruction. So depending on your frame of reference, emphysema could be either just obstructive or restrictive. There's some other variations we can have with our respiratory rhythms as well. For those of you who are thinking of going into respiratory therapy, this terminology will become second-hand nature to you. One of which is apnea, I'm tongue-tied. I can't say the first word right now. So that word at the beginning, that starts with an EU. EU, the prefix EU. U is the root word for true. So if we think of the true, really nucleated cells, eupnea is true breathing or regular, relaxed breathing. And then we can have apnea. The A prefix means without. So apnea is without breath. And individuals that have apnea will spontaneously apnea. It's becoming a very common disease that's associated, or I should say correlated with obesity. Somebody is apnea and have the respirator or the elephant trunk hooked up to their face at night. We can have hypoventilation. Hypoventilation is not enough removal of the CO2. We aren't breathing in and out quickly enough. We can have hypnea or hyperpnea, and this is when we're going to be breathing in and out quickly, not in response to a metabolic demand, but instead in response to a psychological condition when we think of pain being the most common source of that. Exercise can have this occur. This exercise associated with hypnoea is going to be from activation of the proprioceptors, and will be quicker even before we have that metabolic demand change. And then we have hyperventilation. As we look at hyperventilation, as we talked about earlier, it's far and above, in excess of the metabolic demands. It causes us to not have enough carbon dioxide in our bodies. So let's pause for a moment and have a review question. As we are breathing in and out, what is that known as? Is it vital capacity, our inspiratory reserve volume, our expiratory reserve volume, tidal capacity, total lung capacity, or relaxing? So we have about 10 seconds left. If you haven't answered, make sure you get your responses in. So as we look at gentle breathing in and out, or regular breathing or lazy breathing, that is going to be known as our tidal capacity. And it looks like most of us nailed that. Good work, class. Yes, it may be relaxing, but the best answer is tidal capacity. Let's talk about air. Within our respiratory system, this all-important air is going in and going out. And as we are ventilating or moving air in and out, atmospheric air has a known composition. It is about 78% nitrogen and about 21% oxygen. So nitrogen and oxygen are the two biggest components of the gases that we're breathing. But there's some other secondary gases that we breathe in as well. We have a little bit of carbon dioxide, a little bit of argon, some of the noble gases we breathe in and out, not helium, it just floats away. And then depending on humidity and temperature, we can have up to 4% water vapor present in our atmosphere. So we're coming up on winter, and the amount of water vapor in our atmosphere is dropping very rapidly. So this composition is becoming much drier. And as we look at this, the oxygen is what we're going to be most fixated on, but it's worth emphasizing that the nitrogen is important as well. We need to breathe in mostly nitrogen gas. It's a very important thing for us. Nitrogen gas is almost inert. It acts like a noble gas. It has a triple covalent bond binding these two nitrogen atoms together, and this little nitrogen molecule doesn't react with anything in our bodies. It's very non-reactive. And this is good for us because too much oxygen, too much of this highly reactive gas in our bodies could be toxic for us. We're going to camp on this slide for a little bit. I remember when I was in my freshman chemistry class, Dalton's law of partial pressures gave me anxiety attacks. So as we look at Dalton's law of partial pressures, really, let's not even talk about the text. I'm not even going to the slide yet. Let's just go back to this slide. Nitrogen is what most of our air is made of. Now, if our air pressure, let's say, is 1 atmosphere, and most of the air is nitrogen, that means we'll have almost 1 atmosphere worth of nitrogen pressurizing the air. And then the next biggest component is oxygen. And as we look at the oxygen, the pressure, the atmospheric pressure of oxygen is going to be less than nitrogen, because there's less nitrogen in the atmosphere, but it's going to be greater than carbon dioxide and greater than those minor noble gases. All Dalton's law of partial pressure does is takes the overall air pressure and multiplies it by the percent composition of the air. So if we have mostly nitrogen, 78% nitrogen, you take 78% multiplied by the air pressure, and that's the pressure of the nitrogen specifically. And if you have 21% oxygen, you take 21% multiplied by whatever the air pressure is. That's the pressure from just the oxygen. So it's a way of taking overall air pressure and assigning a fractional or proportional pressure to each of the components of the air. And then you add them all up at the end, and you have the total air pressure. So on this slide, we have the percent composition of the major gases in the atmosphere. So the 78% nitrogen, 21% oxygen, then we have a little water vapor, a little carbon dioxide. We take each of those percentages and multiply them by the overall air pressure, in this case being measured in millimeters of mercury. And we find that most of the pressure comes from nitrogen, then followed by oxygen, then water, and then a little bit of carbon dioxide. And all of these partial pressures are totaled at the end, or summed at the end, to give us 760 millimeters of mercury. It seems so easy now, but I remember at the time, it wasn't. So, actually, let's back up one more slide here. There's one more thing I wanted to emphasize. When you see a P and then a gas, that refers to the partial pressure of that gas. And the two partial pressures we care the most about in the respiratory system are the partial pressures of oxygen and the partial pressures of carbon dioxide. Remember, when we look at diffusion, gases diffuse, anything diffuses from an area of high concentration to an area of low concentration. And we'll use partial pressures within the respiratory system to quantify concentration. The higher the partial pressure of a gas, the higher the concentration of the gas. Another way to think of it is just to look at fluid flow. Gases will flow from areas of high pressure to areas of low pressure. So if we have an area with a high partial pressure of oxygen and an area with a low partial pressure of oxygen, that oxygen will flow from the high to low pressure points. So that's atmospheric air, air outside of our bodies. Air outside of our bodies is different from the air inside of our bodies. This is relatively intuitive. And the reason that it's different on the inside of our bodies is because we processed it. As we inhale through our external nares, and that air is flowing over the nasal conchae, and through the meatuses of the nasal conchae, we're humidifying. We are increasing the water concentration in the air. And the water vapor content is going up, up, up. We're also warming it. We're causing the air to expand volume. Well, we're also increasing the proportional volume of water vapor as well. We find that the air that we breathe in has a partial pressure of oxygen, partial pressure of water, that increases about tenfold. And then this time of year, when you exhale, really warm, moist air is then rapidly cooled environment. The water is out of the gas, and you see the tiny mist or the vapor this time of year as you breathe out and see the clouds. We also find that within the alveoli, or those little tiny sacs in the middle of at the end of the respiratory tract, that we're going to be removing oxygen from the air. That oxygen is going to be absorbed into the bloodstream and loaded onto our erythrocytes, or red blood cells. So adding carbon dioxide to the air. So in addition to removing the oxygen, we also add carbon dioxide. What does this mean ultimately? It means that when we breathe out, the air that we breathe out has less oxygen and more carbon dioxide. And when we look at the molar ratios, it's a 1-to-1 molar ratio for the exchange. If we think back to last semester, 6 oxygen gas molecules plus 1 sugar molecule yields 6 waters and 6 carbon dioxides. That equation of cellular respiration. One of the notable things about this is that if you look at the partial pressure of carbon dioxide being 130 times higher, this means that if we start to rebreathe our own air, our carbon dioxide concentrations in our own body will increase very rapidly. And it's primarily a reason of carbon dioxide concentration that we can't indefinitely rebreathe our own air. When we try rebreathing air, we end up having too much carbon dioxide before we run out of oxygen gas. It's typical carbon dioxide that is the limiting factor, and that there's typically too much carbon dioxide for us to rebreathe. Let's pause a second here. How are we doing on time? This is a good stopping point for today. So we're going to stop with alveolar gas exchange. We'll pick up here on Thursday of this week.